Hello, good day, class. Welcome to NMAT-B, the video lecture 1.0. See how this goes. I was struggling trying to get the video to record without the mirror image kept recording, and I'm sure you couldn't have been able to read my writing with that. Anyway, just real quick, we're going through sections 12.1 to 12.3 in class right now, and I will spend the next few minutes trying to fill in some gaps, because we have a finite amount of time in class to cover a whole lot. Hopefully this is a nice supplement to lecture. Please still come to class and read your textbooks. It's only a supplement to lecture, please. Okay, so we've been talking about Fourier series and expansions of functions as linear combinations of an orthogonal set of functions. And I guess some of you may be wondering, what's the point of all of this? And this is the reason for this. Let's explain again what the point of all of this is. So the big question we're asking is, can we expand a function? Or given a set of functions, say phi n, a set of functions phi n that are linearly independent, we want to find out if I can express any function or a given function as a linear combination of these linearly independent functions. Okay? And one of the things that, again, we wanted them to be linearly independent, we want it to be an infinite series. Alright? We want to find out if we can determine the coefficients that make this possible. Okay? One of the things that I hope that you guys understood from lecture is that, so we discussed orthogonality, and we've been playing around with those integrals, but I wanted to have you guys get this down, that if a set of functions are orthogonal, right, if you prove that they're orthogonal, you've proved that they're linearly independent. Okay, so orthogonality implies linear independence. However, linear independence does not necessarily imply orthogonality. Remember this is very crucial, right? If I have a set of functions that are linearly independent, they may or may not be orthogonal. But if they're orthogonal, they are linearly independent. Again, think about the vector analogy. If I have three vectors that are linearly independent, say I, j, k, right? Or rather, that are orthogonal I, j, k, they clearly are linearly independent. But if I have three other vectors that are linearly independent, they're not necessarily orthogonal, right? Orthogonality in vectors means they're perpendicular. They're not necessarily perpendicular. The same kind of thing here. Orthogonality implies linear independence, but linear independence does not imply orthogonality. So if I have a set of functions that are orthogonal, then I've shown that they're linearly independent, and in theory I'm proving that I can have that series expansion. It's a complete set because they're linearly independent and they're orthogonal. Okay, so for those of you who missed lecture, what do I mean by orthogonality? Before I start throwing those words out there, orthogonality just comes from a definition that we gave in class for the inner product of two functions. So if I have two functions phi n, and I find the inner product, this is what we use to notate inner product, by the way. I find the inner product, which is defined as the inner product over an interval a, b, is defined as the integral of the product of those functions. This integral right here. So if I find out that this inner product equals 0 for n not equal to n, then we have an orthogonal set. Okay? We also talked about if I have an inner product of a function with itself, and we said that this is just simply the square norm of that function. Okay? So what we're saying is that a function with itself, inner product should not be 0, obviously. But for any other function in the set, we have 0, and that shows that it's orthogonal. Okay, or it's an orthogonal set. And if we have an orthogonal set, there's some interesting trick which we've played with. I guess before that, I can show you an example of how to work with this notation. If I have, say, the sum of these orthogonal functions, right, and I want to find an inner product of this sum with another function, find m of x, what I do is I have a to b, and the interval is from a to b. The interval is always very crucial in finding inner product. In talking about orthogonality, they're crucial. Getting the interval is crucial. I'm sorry. So this sum in here times this is just simply phi m of x times phi 0 plus phi 1 plus phi 2 and so on and so forth dx. And because we can split integrals into sums, we have phi 0 phi m of x plus phi 1 phi m plus phi 2 phi m and so on and so forth dx. So I can express this as just simply phi 0 phi m plus phi 1 phi m and so on and so forth, right? So the inner product of this sum with phi m, the inner product of the sum with phi m is just simply the sum of this inner product. Okay, so I'm going to be using short form notation, all right, just to make things, clearer, less cumbersome. So please understand how we show that. So the trick that I was talking about, by the way, if I have an expansion f of x as such, as a combination of these linearly independent functions, and I take the inner product with one of those functions, then I get this. Right? This is what I just showed you right now. And I already know that orthogonality means that the inner product of this function equals 0 for n not equal to m. So f phi m has to equal 0 for everything except when n equals m, right? Which is phi m, okay? There's plus phi 0, phi m, phi 1, phi m, phi 2, all of those other ones go to 0. Times cm, right? So I can determine the coefficient cm as f phi m over phi m over the inner product of this function. And we already called this the square norm of phi m. So this series is possible with Cn equals f phi n over the square norm of phi n. Okay? This is called the generalized Fourier series. So when is this possible? Just like we talked about in chapter 5, there are important things that we need to analyze for a series when we're trying to represent a function using that series. The series have to be convergent, right? And the interval of convergence of that series is the domain over which this function can be represented. So if over that interval we just work with AB, if over this interval the series is convergent, then we can describe f of x over that interval. Another important thing, so I'll just wipe this off, I'm sorry. Another important thing, well, first of all, we want convergence of the series. Another important thing is that the functions have to be integrable, right? F of x and phi m of x. If we're trying to find the inner product, we have to have them integrable, right? So f of x and phi of x are integrable within the interval of that we're interested in. Okay, what does that mean? I can have a function like that has, say, an infinite discontinuity, something like this, let's say, right? So that at zeros has an infinite discontinuity from -1 to 1. This is not a function we can find the integral of, right? The area under this curve is infinite because of the infinite discontinuity. So if f of x, phi m of x, or f of x, or f of or phi of m of x, if any of those functions that have infinite discontinuity, we can apply this method. However, if it's a finite discontinuity, it's possible, and we'll explain. We'll talk about that in a bit. This is fine, right? The area exists. Okay. So this is crucial. These two are crucial. And if those things are possible, if those two conditions are met, then the series converges, and we can represent it as a generalized Fourier series. So we looked at examples in class on again. This is just real quick. This is the whole point of this all. Can we expand a function in terms of a series? It's a series convergent. It's the kind of coefficients we found out using the technique we just showed. Okay, so we talked about the a set of linearly independent, a set of orthogonal functions that we were able to use for expanding Fourier series, Fourier sine and cosine series, and our expansion came out to look like this. Over an interval minus p to p. Alright, our orthogonal set of series were 1 sine n pi x over p and cosine n pi x over p. Now, the coefficients, using the same orthogonality trick we just talked about, if we found the inner product of this function with any of those orthogonal functions, we can find their respective coefficients. So we found out that a naught over 2 equals 1 over p integral from minus p to p f of x dx, which is the inner product of f of x with respect to 1 divided by the norm, which turned out to be p. That for bn, for the bn coefficients, was 1 over p minus p to p of sine of f of x times sine n. In other words, the inner product of f of x with sine n pi x over p. Okay, we showed this in class, so I'm just refreshing your memories here. And the an, the same integral, the norm with the function, or the inner product with the function f of x divided by the norm. So, given a function f of x, I believe that if conditions are met, these conditions are met, I should be able to express it as a power series, or sorry, as an infinite series of the linearly independent functions, of the orthogonal functions here. Okay, so, wow, this is infinity, by the way. Okay. Let's pause right here, just because I don't think I'll have enough time to go through examples. Well, this is just a test run anyway. I had a 20 minute period where I could do this. Some important things that we can talk about again in class on Monday. But please look through this and solve problems. I guess real quick, I still have about 4 or 5 minutes. If I have a function, and your textbook has good examples, I don't know why I should. Why not? Let's solve an example from the textbook. If I have a function as, say, f of x equals 1 and x, going from minus pi to and I want to find the Fourier series expansion of f of x. All again I need to do is I need to show that I can do something like this. Go from 1 to infinity. A n cosine n pi x over p plus b n sine n pi x over p. First thing you want to do is find out what these coefficients are. And we already have a very handy formula that we can work with. 1 over p minus p to the p f of x. Let's start with that coefficient. What is p here? It's simply what we have from our interval, minus pi to pi. So p is pi. Okay? 1 over pi minus pi to pi f of x dx. But f of x is, if you look at this function, f of x looks as such. Sorry. As such, right? It's 1 for minus pi to 0 and x from 0 to pi. So we have some discontinuity here, right? But the area exists because it's a finite discontinuity, right? How do we do this from calculus? If I have an integral of this form, we just split the integral into two integrals, right? From minus pi to 0 and 0 to pi. So I have a naught over 2 equals 1 over pi integral of minus pi to 0 of 1 dx plus 1 over plus integral of 0 to pi x dx. And that gives us 1 over pi. Integral of 1 is x, from 0 to minus pi is pi. This is x squared over 2, from 0 to pi is pi squared over 2. And we have our first coefficient. If I made a mistake, I'm sorry. I just made this question up, so I haven't solved it. But the idea is to determine each coefficient using this equation, this formulas from the orthogonality trick that we derived. Once we have those coefficients, we can verify if the series converge. For the most part, the functions that you're going to work with here will have series that converge. But again, this is the goal of the whole section here. And we'll go into more details of some other examples, some other key things that I would like you guys to pick on Monday. But please go through this, go through your textbook, solve some questions. It's pretty easy from here on. It's just integration, which you're already masters of. And then the key ideas behind expanding Fourier series, I hope you picked from this. If you have questions, please ask me, and I can fill in some more gaps on Monday. Thank you.